Again, I want to thank you for joining us today for our Apparatus webinar titled SQL 2014 Enhancements. Before I hand things over, I would like to briefly introduce our 3 Microsoft certified professional speakers from Apparatus. Starting with Frank Gill. Frank has worked in various SQL Server DBA positions throughout his career. Frank has worked for companies in a variety of industries and has experience with a wide range of tools, technologies, and concepts. Kyle Nair currently leads all SQL Server database projects at Apparatus. Over the course of his career, he has worked or consulted for hundreds of companies spanning Fortune 100 to startups. In addition, he has significant technical depth in several areas of information technology. David Kincaid supports the business intelligence team in delivering high-performance analytical and decision support solutions. He has over 5 years' experience assessing and building out enterprise data solutions. I just want to give a disclaimer that this webinar is going to be recorded. Following the webinar, we will have time for questions and answers, but feel free to type in any questions that come to mind in the chat section throughout the webinar. And now I would like to hand it over to Frank, who will start out our presentation.
Good afternoon, everybody.
Hi, Frank.
Hello. Give me 1 second here. All right. So I'm going to talk about in-memory OLTP, which is a new feature in SQL Server 2014. I'm going to cover why it's faster, reasons to use it, and then I'm going to talk about limiting I/O and resource governor, which is a new feature in SQL Server 2014. And then finally, I'll talk briefly about buffer pool extension and delayed durability. So in the current world in SQL Server, all database operations access data using 8K pages, which are resident on disk. Anytime SQL Server needs to do anything with data on one of those 8K pages, it needs to be read into memory. And it's processed in memory, and then it will be written back out to disk at some point. And when transactions run and data is updated, inserted, deleted, there is a transaction that begins and commits. And when that transaction commits, the log records associated with that transaction are hardened to disk. And this can cause a couple of different bottlenecks. The first two deal with the pages themselves. When the page is read into memory and it is being modified, a lock is taken on that page. And if another process is attempting to update, insert, or delete to that page at the same time, or select from that page, depending on your isolation level, the page is going to be locked, and that second process will be blocked. The second thing that will happen is once that page is in memory, SQL Server takes what's called a latch on that page as the page is being updated. You can think of it as a lightweight lock to protect that page in memory. And if you have heavy activity on a specific page or a group of pages, you can see latch weights on those highly accessed pages.
Hey, Frank, on that one, so if your database fits in memory already, what's the advantage?
So if your database already fits in memory, all of the pages have been read from disk into memory, but you're still going to have potential locking and latching issues in memory because it needs to protect that page for the duration of any activity hitting that page when it's in memory. And I'll get to how it works in in-memory OLTP in a minute, and I'll be able to explain the difference and explain why in-memory will get you past this issue.
Great.
So the other issue that in-memory OLTP will potentially get you past, another bottleneck, is the concept of write-ahead logging. So once a transaction commits, you've read your pages into memory, you've made your change. As soon as that transaction commits, the log records associated with that transaction are written to disk. And it's basically, you have one log file, everything's hitting the same log file, so log writes can become a bottleneck if you have a system with really high transactional volume. So the way that in-memory processing works is the concept of data pages no longer exists with an in-memory table. Basically, the data is read into memory and it resides in memory. And as modifications are made, a new version of the row is created in memory. And the row versions are time-stamped. And as transactions come into process, it goes to look for the row. If it sees multiple versions, the transaction knows what its timestamp is. It knows which time-stamped row is valid for it. As a result, locking and latching are no longer an issue because the transaction is only going to be hitting a single row. And speaking to the log write bottleneck, when in-memory transactions write, they only write a single row to the log file to reduce that log write contention. For example, if I do an insert of 100 rows to a table on a disk-based table, and I look in the transaction log, I will see 100 insert statements in that log. If I do the same 100 inserts to an in-memory table, I'll see a single insert row.
Hey, Frank.
Yes.
You keep talking about this in memory. So
Yep.
How does all this stuff get in there?
So when the instance starts up, you're going to load the data from disk. Oh, I should say that when you create an in-memory table, you have two durability options. You have schema and data, which means that when the instance shuts down, SQL Server will harden the data that is in memory to disk. Schema only is your other durability option. If you have schema only set, when an instance shuts down, all of the data that you've got in memory is going to be lost. If your durability is set to schema and data, when the instance starts up, it is going to read all of that data into memory. Does that answer your question?
Yep, thank you.
You're welcome. So this is a simplified version of what the in-memory row structure looks like. So I've got my begin timestamp, my end timestamp, and then a row payload. The row payload is going to be the data that's actually included on that row. And when I do an insert to an in-memory table, what I'm going to see is my begin timestamp is going to be populated. Microsoft is using the infinity symbol for a null timestamp, or if there is no expiration on this row. So I've done an insert. This is the only version of this row in memory. If I update this row, SQL Server is going to generate a new version of the row and load that into memory, and it's going to update that begin timestamp, set the end timestamp to 10, which is the begin timestamp of my previous row. So if a transaction comes in and it has a timestamp between 0 and 10, it's going to see that initially inserted row. If it has one between 10 and 20, or actually 10 and greater, it will see the updated row. And as additional updates, changes happen, you'll get multiple versions of this data in memory, and transactions know which one to look at. So that explains how the mechanism works. The reasons for using in-memory OLTP are a few. Applications that require both transactional speed and volume are a use case for this. If you have objects that are experiencing excessive blocking and latch weights, or if you are seeing log write weights as an issue, in-memory can help you solve those problems. One other thing to point out is that you have the ability to mix both disk-based and in-memory objects in a database. So if you have a single table that is causing you pain, you can put that table in memory and leave your remaining tables on disk. So it allows you to pick and choose and makes things simpler to remediate issues. So that's what I've got for in-memory, and I'll talk about limiting I/O with Resource Governor next. So Resource Governor has been around since SQL Server 2008, and prior to 2014, it's allowed throttling both CPU and memory. The issue with that is that CPU and memory on most modern systems are not generally a problem I/O is a bottleneck on a lot of the systems that are out there today. So in 2014, they've changed SQL Server to allow you to throttle I/O. You can set both minimum and maximum values for I/O, and this means that I/O levels can be guaranteed for mission-critical applications, and you can set thresholds for users or applications that you want to limit. If you want to limit for ad hoc queries, if you want to limit for a reporting application, you can do that. And I will show you how that works. So I have a database out on my system, and it has a single table in it that contains 5 million records. And I am going to show you the process. I've set the resource governor features up, but I'll step through the script, and then I'll run through the demo to show you what it looks like when the I/O limits. So the first thing that you need to do when you're setting up resource governor is you need to create at least one resource pool. And in this case, I've got two of them. I've got a restricted I/O pool and an ad hoc I/O pool. And I've set the max IOPS per volume for restricted to 30. And for ad hoc, I've got it set to 10. So that's going to limit these to 30 and 10 IOPS per second for resource pools. After that, you need to create a workload group for each pool. And I've got restricted I/O group and ad hoc I/O group. And then the third thing to do is create a function. And the function is what tells SQL Server which of those groups to use. In this case, if my username, the username that's logged on and connected, is restrict my I/O, it's going to use that restricted I/O group. If the query is coming from either Management Studio or Query Analyzer, it's going to use the ad hoc I/O group. And if it doesn't fall into either of those buckets, it's going to use the default. So I have Perfmon open, and it's a new set of counters in Performance Monitor with 2014 specific to the resource groups. And I am looking at disk read I/O per second, because that's what I have limited. And I've got 3 instances of the counter out here, one for each of my groups, ad hoc I/O pool, restricted I/O pool, and default. So my table with 1 million records, or 5 million records, all I'm going to do is select into a temp table from that. And I am currently connected here as ad hoc user. So let me highlight, make sure ad hoc I/O pool is selected. I execute this, it's going to start to run, and you will see this. It peaked at 11, but then it dropped down, and you can see that my I/O is maintaining right about 10. It will fluctuate right around there. You'll see it jump to 11, maybe drop down to 9, but it should maintain right in that range for the duration of this query. The query is going to run longer than I want it to. So I've demonstrated that limit. I'm going to stop this query, and I am going to clear out my buffer cache just so the next, if I have the correct connection, give me 1 second. I just want to make sure the next one has to work as hard as that one did. So I'm going to run the same query, and in this case, I'm connected as restrict my I/O, and if you remember, that's set to use 30 IOPS per second. So if I execute this, it's going to start clicking. If I highlight that, you'll see that this jumps to 30 and is running pretty much straight across. My maximum is 31, but it will maintain right about 30 for the duration of the transaction. Once again, the 5 million inserts is going to take longer than I want to have you watch the graph, so I'm going to stop this. And the final thing I'm going to do is, because of the way I have my function structured with default at the bottom, if I run something under a user that is not one of these two through Management Studio, it's going to hit this. So to hit the default, I'm going to execute a job, and the job is doing the same query that insert into the temp table, but this will give you a sense of what happens for something that isn't restricted. So let me start this job, flip over here, and highlight that. And what you'll see here, because of the way Performance Monitor works, each one of these counters has a scale. So these are all set to a scale of 1. So this line is sitting at the top of the graph. The reason for that is because of the scale of 1, the highest number this graph can represent is 100. But if you look over here at maximum, it grabbed almost 1,000 IOPS per second when it started, and it has been grabbing more than 100, and it is now done. So where those other queries with the limited I/O would have run for much longer, this one did those 5 million inserts in the select into statement in about, how long did that run? It probably ran about 5 seconds. So that is a quick demonstration of how Resource Governor works. From there, I'll flip back to the slides and talk briefly about buffer pool extensions and delayed durability. So buffer pool extensions, I talked about SQL Server writing everything, all the pages that it's going to modify are being written into memory. And in systems prior to 2014, you had those pages resident in memory, and you had pages resident on disk. Anytime that you needed to modify a page, it would be read into memory, and then it would be written back to disk. Buffer pool extension allows you to allocate SSD storage to your SQL Server instance to extend that buffer pool. And this basically acts as a cache. So pages are read from disk into memory, and then they are flushed to the SSD storage, which is a much faster operation than hitting a traditional spinning disk. And it also allows a page to be pulled back from SSD more quickly if it needs to be pulled back into memory. So it increases the capacity of your buffer cache, and it increases the speed of the retrieval of pages from the buffer pool extension. And then the final feature I'll talk about is delayed durability. So when I was talking about in memory, I talked about the idea that as soon as a transaction commits in traditional SQL Server, the log records associated with that will be hardened to disk. And if you have a system with high transactional volume, that log write can be a bottleneck. There's a feature in 2014 called delayed durability, and basically what this does is it batches those commits. Rather than a transaction writing those log records to disk immediately, it will batch them into groups of about 60K, and it will write them out in those batches. So it, once again, will help minimize that log write as a bottleneck. The pro to this is it reduces the log contention. The con is that data loss will occur if your system comes down, because you will have some number of transaction records that cannot be written. And in SQL Server, transactions are atomic. You can't have a transaction stop halfway. So if you have written some transaction records to the log for a transaction, your system crashes and you lose the remaining log records for that transaction. When SQL Server comes up, it will not, none of that transactional activity will have been hardened, and you will lose that data. If you are in a situation where that level of data loss is acceptable as a trade-off for the speed and the performance gain you're going to get, delayed durability is something that you may want to look at. And that is what I've got, and I'll turn it over to Kyle to talk about taking SQL to the cloud.
Thank you, Frank. So one of the pushes that Microsoft has been doing is trying to get both on-prem and cloud solutions to be to integrate well. And with SQL 14, they've taken strides to get us there. And so we're going to be talking about a few of those features that are in SQL 14 that haven't existed prior. that move us closer to that seamless hybrid environment that we may want to build. So there are several Azure technologies to talk about. There's the SQL Azure, there's infrastructure as a service, there's all sorts of web applications and storage. We're going to call out two of those technologies today, which is really where SQL Server 14 has leveraged. The first of those is the Azure Blob storage. So essentially this is just data storage in the cloud for you to leverage remotely. So that's the Azure Blob storage. And SQL Server 14 leverages this in two ways. And the first way is by putting a database on a blob. So I don't know how many times I've had people come to me and say, I'm trying to put my database on a network share, and it's not working. I want to create my database, and I want the file to be on a network share. You can't do that. Actually, you can now, and it works. And you can do it on an Azure Blob as well now. So if you think about putting your database files out in the cloud, the pros here are easy, high available storage. So if you don't want to have to worry about getting your own replicated SAN environment set up so that you have highly available storage, you don't have to think about that because you're just pointing it to essentially a URL that then when you point to that URL, the file just stays in the cloud for you. So it's highly available by its very nature. Ease of migration. So if you ever need to migrate to different servers or migrate from on-prem to the cloud or migrate from a infrastructure cloud OS to another cloud OS, having the database file actually be on the blob storage can significantly decrease the amount of effort involved to have to migrate that server. So if you think about it, if you were able to simply detach the database from one location and attach it to another location, to another server, at the exact same location, your downtime for that migration would be very minimal, but you'd be able to do a full migration to a different server with relative ease. And then security. So if you implement TDE, or transparent data encryption, generally speaking, the key that you need is stored on the SQL Server instance. So if someone has access to the SQL Server instance and they have access to your data files, through a lot of work with the computer, they may be able to figure out how to get to your data. But by putting your data files out onto the cloud, there is absolute separation between your data file, which is fully encrypted, and the key which decrypts it on your server. So you can increase your security, you can increase your separation by putting these databases out on the blob. The cons here are performance. So performance and bandwidth here are going to kind of go in the same. If you can afford to get a full 100 meg connection to Azure, then you get 100 meg bandwidth on performance. And I'm using that as an exaggerated example because that's a very large internet connection. But when you're dealing with 4 gigabit and 8 gigabit, 10 gigabit, and 40 gigabit connections with InfiniBand for connecting to large SANs, if I/O performance is your primary driver, this may not be a good option for you because you are going over the internet to get to this information. Bandwidth falls in line with here. So if you are going to do this, you have to make certain that you have the bandwidth available on your on-prem solution to be able to communicate with those database files as well as you need it to perform. So your I/O becomes a bigger issue than it does if you're on storage locally. So you have to make certain that you size your bandwidth appropriately. And then cost. So cost here it may be a pro, it may be a con. I put it as a con, primarily because you are paying for all the data that you push into Azure, as well as the data that exists there. So if you think about paying for this, you're paying for the activity as well as the actual storage itself. So it may be cheaper than acquiring an on-prem solution, but it's something to think about. And I wanted to call that out here for you to think about when you think about putting databases out on the blob, that you are going to have to be paying for that traffic as well as the actual storage sitting there. and that's the trade-off you're going to get when you do move to a cloud solution.
So Kyle, with those pros and cons, can you give a use case where you would go with this, backing up to the cloud?
So a database on the cloud would probably be like an archive database, where I need it to be available, but performance isn't key, and I'm not changing it that much. So I would just functionally be paying for storage. I wouldn't be paying to push data to it all the time because it's not changing. And it would always be available, and I don't have to worry about finding cheaper storage within my infrastructure to put on. So that would be probably a good place to use this. And if I'm planning on eventually moving to Azure, putting it there first, if you can deal with the performance and the cost, will make your migration to Azure significantly easier, because then all you have to do is install SQL Server up there in the cloud and then attach those database files that already exist. Does that help?
Yep, thank you.
Awesome. Back up to the blob. So the same Azure blob storage. With SQL 14, we can now initiate a backup to a URL. So before, with backups, we had virtual devices, and we had file devices that we could send to, and we had backup devices that we could create. And now we can actually take a backup directly to a URL. And what that allows us to do is to say, hey, SQL Server, back up this database directly to the cloud. So we can now say, take our backups that we want to have off-site and back them directly into our Azure storage. So we have highly available and incredibly disaster-resistant storage available to us, so that if our on-prem solution does die, our data doesn't die with it. So if you do have to have a situation where you need that off-site, you don't have room in your secondary data center, or you don't have a secondary data center, but you want to get those backups off-site, you can leverage the built-in tools within SQL Server to push that out to Azure to get the backup there. In this case, the cons are the same. Bandwidth, it's got to be fast enough to make you happy. So if you're pushing through too many transactions for your log backups to fit through your bandwidth between each log backup, you're going to miss log backups. So you have to make certain that you're sized appropriately to push this up into the cloud. And once again, cost is you're paying for storage, and you're paying for the bandwidth to get it there. So that's backing up to the blob. So extending your infrastructure. So with the Azure Blob storage, we're essentially saying we have a storage pool sitting out there somewhere for us to use. We could also extend our infrastructure into the cloud, and Microsoft has made this incredibly easy with SQL 14. And really, it is all you need is connectivity. So if you have connectivity out from your SQL box out to Azure, you can easily set up geo-redundancy with an availability group. So with SQL Server Enterprise Edition in 2012, they introduced to us the concept of availability groups, which gives us SQL Server listeners and gives us the ability to have database sets that fail together between different SQL Server boxes. With the Add Azure Replica that Microsoft has built in now, what will happen is that you can go there and it will provision the virtual machine that you choose on the fly. So you don't have to worry about having a VM set up there. You don't have to worry about installing SQL Server. You go through your on-prem management studio and it will go create the VM, get SQL set up, and then add the databases to the availability group and get that set up for you. It's very awesome, very easy to use. So it makes this really an easy to set up. And then also from a migration strategy, if I'm trying to migrate to the cloud and I want limited downtime, you can use this functionality, create your VM out there through this process, have it set up your availability group, and then once you get there, fail over to your secondary, and now you're in the cloud. So you can get rid of your primary at that point. The listeners are already there. Your network's already set up, and you can move stuff to the cloud very quickly through using this solution. So the cons here, I think you're seeing a theme. We're talking about bandwidth. So if you have I would not recommend making these synchronous replicas. But if you have to have synchronous replication, then you're dealing with bandwidth and latency there, and so your transactions may slow down on the primary. And with async, you may lag behind because of your bandwidth. So you have to make certain you have enough bandwidth to feed your replication. And then the cost of both the storage sitting there, the new virtual machine it spins up, because as soon as it spins up that virtual machine, it is now on your account and you are paying for it. So it's creating a virtual machine, it's spinning up storage, and you're storing those databases up in the cloud as well.
So Kyle, I think I heard you right on this one, but does it actually require an existing availability group, or are you creating that on the fly?
So you need to have an availability group created on-prem, and then you can extend into the cloud from that availability group. So you are functionally adding a replica to the availability group. So you create the availability group, and then you just add a replica that happens to be in Azure. Does that help?
Yep.
So with that, that's all I have for the SQL in the cloud. So I'm going to hand it over to Dave here, and he's going to be talking about BI enhancements in 2014.
All right, thanks, Kyle. So comparatively, I would say the SQL Server core platform went under a number of changes in SQL 2014. On the BI side of the house, I would say they didn't give us quite as many new features. I'll say there's really 2.5 notable new ones. Number one being SQL Server Data Tools is now available for 2012 and 2013. So those of you working on your integration services packages, analysis services, reporting services, you can now do that with the newest version of Visual Studio. The half point that I give them is on Power View. So in Power View in 2012, before Service Pack 1, you could only do Power View on top of a tabular model or Power Pivot model. Now in SP1 on 2012 and then in SQL 2014, we can now do Power View on top of multidimensional. So those of you who have the multidimensional from years past can now use Power View directly against that and have essentially the same experience. And then probably the most notable number of different changes to the Columnstore index. Biggest one now being that Columnstore indexes are updatable. So in 2012 you had to disable your index, insert or update your rows, and then re-enable or redeploy your index. So for those of you who haven't used Columnstore in the past, a little bit of background. So it's really Microsoft's attempt at columnar database functionality. So you take your standard row-based table, essentially flip it on its side, and are now storing the columns instead of the individual rows. In 2012, this was present, except for you actually had to essentially do a copy of your data. So you would have your standard table, it could have its standard indexes, and you would do a non-clustered Columnstore index on top of that to take advantage of the Columnstore performance and functionality. I'd still say its biggest use case both in 2012 and 2014 is on your data warehouse type queries and loads, most notably probably your really large fact tables. The improvements in additional performance that you're going to get are going to be on those really large fact tables that are not undergoing a lot of inserts and updates. Where you get that performance from, though, is actually largely based in the compression. So by flipping it into those Columnstore segments, you're getting all of your like data. So data that's resting in those column segments is actually all of the same type, so you get very, very good compression. And therefore get a lot more into memory, which is just going to help out your overall performance and require less I/O to go and get that data. So in a little bit more of a pictorial format, I've got my standard table over here on the left, just standard rows. As soon as I put that Columnstore index on that table, it's now splitting those rows into a column. So each column is going to get its own segment within that row. And then as you compress that, essentially the more non-unique your data is, the better compression you're going to get. But either way, you should expect some pretty significant compression here. I've seen anywhere from 5x to 15, depending on what you're working with. Another really great advantage is, when you're writing a query against a row store, it's got to parse through all those columns. When you're working with a column store, essentially it's only going to go after the segments or columns which you're including in your select clause of your query. So if I only select 2 columns, I may have 20 different columns in my column store index. It's only going to have to go after the data for those 2, again, saving me a ton of performance because it can easily load those into memory and I'm off and running. So what's new in 2014? So again, most notably here is the updatable column store index, also referred to as the clustered column store index. Additional data types are supported, so probably the 2 notable ones in SQL 2012 were just your numeric and decimal. Large numeric and decimals you actually could not include within this index. Also getting a lot better batch processing, so Microsoft did a number of things to refactor how that query engine operates against your column stored indexes. You used to have to write it a very specific way, very standardized way to really take advantage of the column store. They've done a number of things to make that more inherent. And then lastly, for those things that you're really only archiving, let's say you've got to keep a certain number of years worth of data for some sort of compliance or audit requirement. We've also introduced Column Store Archive, which gives you even better compression for that data that you need to use more infrequently. So standard partitioning schema, throwing that, if you're doing it by year or by date, essentially taking that historical data, doing Column Store Archive so that it's compressed on disk.
Dave, with the compression on the Column Store Archive, is there a CPU hit for that? I know that with row and page compression on the SQL Server side, that's the concern that you need to be worried about, is the CPU processing it takes to compress and uncompress that stuff.
Yeah, so great question, and answer is absolutely. So again, the big caveat here is really you only want to use that Column Store Archive type compression for that data that you think you're going to be using more infrequently. I would still expect decent performance depending on what kind of query you're throwing at it, but certainly going to take a processor hit as that data gets compressed and uncompressed. That answer your question?
Thank you. Yes, thank you.
All right, so hitting on it just a little bit more before I get into a demo here. So a few caveats with the 2012 to 2014 switch. So, biggest pain in 2012 is you put the column store index on your table. Typically, it's going to be like a fact table that you may be updating a few times a day, maybe once nightly. So if I wanted to do that in 2012, as soon as I want to insert those new records, I had to disable my index, write all my rows in, and then rebuild that index, which, depending on the size of your table and how you're partitioning, can be a lengthy process. In SQL 2014, I don't have to worry about doing any of that mumbo-jumbo at all. I essentially am just inserting my records, performing my update statements, performing my deletes, and I'll say that Microsoft is doing a lot of fancy trickery in the background to make that happen. 2 other caveats with this. In 2012, it was a non-clustered column store index, so you could combine that with your other standard indexing schemas on the table. In 2014, if you use a clustered column store index, it can be the only index. So just something to keep in mind. Again, the performance improvements you're getting with the column store index are going to be leaps and bounds ahead of any other indexes you could employ, but you can't put 2 in place. And then the other big thing, only supported in enterprise and developer editions. So the fancy trickery I talked about. So how did Microsoft achieve this updatable column store index? Really in a number of different ways. So they've introduced what's called the Delta Store, which means if I've got a 20 million row table, let's say I've got 20 million rows already in place, I want to insert another 1,000. Those 20 million rows are going to exist in the column store, but those new 1,000 rows that I insert are actually going to go into a temporary row store table. That's whenever I run a query, all that data is still available, but it's actually hitting 2 different spots. So it's hitting all my actual column store data, as well as going to this Delta Store to figure out any additional records that it needs to get. So those Delta Stores typically exist for about 1 million rows. That's just the way Microsoft designed it, so that once you hit that 1 million row, that Delta store essentially is going to get closed, and then a background process is going to come through, add that to your column store, and then as new records are inserted, a new Delta store gets opened. So all that's being handled behind the scenes for you in those background processes, but again, some fancy trickery here to really achieve that updatable column store. Also, a little note of point here. So from a delete perspective, again, fancy trickery here. They've actually developed a means that it really does logical deletes in the background. So when you run a delete statement on a column store table, it's going to essentially hide those records unless those records exist in the Delta store. So there they get deleted physically. Otherwise, it's more of a logical delete that those things are hidden until you then come around and rebuild that table down the line. So something to keep in mind. Again, pictorial representation here. So act like I'm loading all my rows in. My initial loads, those are getting broken into their column segments, getting put into the column store. Then as I come back around and add additional rows, you'll see that those rows are added to the Delta store. Again, just a row store table that exists behind the scenes that is completely meant to be temporary. Another thing I noted was just the additional data types. So in 2012, could not do binary, bar binary, most notably the decimal and numeric large numbers. In SQL 2014, we now have all these capabilities. However, we still have a few that it does not support, mainly being those varchar maxes, in case you're using any big descriptors in some of your tables. Also, the refactoring Microsoft did on the 2014 engine just to take advantage of the better batch processing. The most notable one in 2012 was with outer joins. It would not take advantage of the column store index when you did an outer join. Now in 2014, they have added in that functionality. And then the last piece I talked about was just the additional column store archive compression. Again, I've seen you typically get anywhere from 5 to 20% on your column store index. Column store archive can really push this up to another 2 times. So if I'm getting 15 times compression with column store, I could get potentially up to 30 with my column store archive. So just a way to keep that old data in the database but utilize as much space as possible.
So I got a question. So I've got a company that sells kumquats, and I want to keep track of like last 10 years of sales. When you compress this using this column store archive, so I know it's never going to change, does that actually go down to disk, or is it only in memory that's compressed?
Yep, so that's going to be compressed both on disk and in memory. Again, the biggest thing to keep in mind on this one that Frank mentioned earlier was just, what's your CPU hit going to be whenever you're compressing and decompressing that if you do need to go after that historical data. Does that answer your question?
Thank you.
All right, so now time for a quick demo. Alrighty, so I've got a couple different tables here to show off both the storage compression as well as really how that column store works and how the performance gains that you can get out of it. So I'm in a SQL 2014 table right now. I've set some statistics on so you guys can see what's going on. Proof that I'm not lying that these are approximately about a 20 million row table. I've got one that has no column store index on it, one that does, and then one that has the column store index archive compression enabled. So not a complex query by any means, some basic sums using some facts and dimension tables. Takes about a second. Certainly a fine query in terms of performance and speed. You can see it did about 100,000 reads. Well, when I come over to my column store index, you're going to notice that this is almost instantaneous. If I go back in there, you'll notice that it only had to do 6,000 reads. So significantly less reads. Again, with that data getting compressed and into memory, it has to do significantly less I/O. You'll also notice that my milliseconds here is 7 milliseconds, so again, almost instantaneous. Another thing, I can prove these ones out as well. So when I started with my original table, it was about 840 megabytes 20 million row table, makes sense. Employing my column store index, my storage size went down to 105 megabytes, so about an 8 times compression there. As soon as I put that archive compression on, I get an additional 17x compression, so I'm down all the way down to 47 megabytes. So if you think about that in really, really large tables, again, historical data that you don't need to access very frequently, certainly makes a lot of sense for that compression to save that space on disk. Biggest feature, again, just being, yay, I can now write records into the column store index. Before, I would have had to disable, do my batch update, do my batch insert, re-enable that index, and then be on my way. And what you'll notice here, if I look at the actual nuts and bolts behind this table, there's a Delta store that has been opened. It's got 5 records in there. Those 5 records are going to continue to exist within that Delta store until it gets closer to that 1 million row mark, at which point some background processes will come through, pick that table up, and put it into the column store. In comparison, here's a SQL 2012 instance. I've got a table in here with a column store index on it. As soon as I try to write, you're going to notice insert statement failed because that's not possible in 2012. So I would have to go in my script or in whatever database process I was using to always include these alter index statements to make sure I disable and then insert and then rebuild. So, from a personal perspective, a great feature to be able to directly insert and update and delete directly into my column store table. With that, turn it back over to Mary Beth.
Great, thank you. At this time, if anybody has any questions, we are open for those. All right, well, if there are no questions, then we will go ahead and wrap things up. Frank, Kyle, and Dave, thank you for presenting the webinar. Following the conclusion of the webinar, we will make sure to send out a recording of the presentation to anyone who is registered for the webinar, as well as posting it to our blog, which I will post a link of here for you. But it's apparatus.net/simplifyit if you'd like to check that out. Thank you for attending.